Good morning, children. Today we will discuss about Poisson's brackets. Let us go with the presentation. Poisson's brackets. So here let us consider two functions, capital F and capital G, and these two functions depend upon position coordinates small qk, momentum coordinates small pk, and time t. The Poisson bracket of f and g can be defined as f comma g with respect to q comma p, which is equals to sigma k equals to 1 to n dou f by dou qk dou g by dou pk minus dou f by dou pk dou g by dou qk. So here these two functions f and g depend upon momenta and these position coordinate and momentum coordinates dou qk and dou pk. So for let us we may drop these subscripts and write the Poisson bracket as f comma g. So total time derivative of the function f can be written as df by dt, which is equals to dou f by dou t, plus sigma k equals to 1 to n dou f by dou qk q dot k plus dou f by dou pk into p dot k. So by using the Hamilton's equations, we have q dot k is equals to dou h by dou pk and minus p dot k, which is equals to dou h by dou qk. Let us substitute these q dot k and minus p dot k in equation number 6. If you substitute, so here df by dt, which is equals to f dot, which is equals to dou f by dou t plus sigma k equals to 1 to n dou f by dou qk, write as it is, and substitute qk, which is equals to dou h by dou pk minus dou f by dou pk into pk is p dot k is nothing but dou h by dou qk. So in the view of the definition of Poisson bracket given by the equation number 5, we obtain df by dt, which is equals to dou f by dou t plus f comma h. So this is in the form of Poisson bracket f comma h. So from this equation number 8, we see that the function f is a constant of motion only if df by dt equals to 0 or dou f by dou t plus f comma h is equals to 0. That means here when LHS equals to 0 or RHS equals to 0, then the equation we can see the function f is a constant of motion. Now, if the function f does not depend on time, dou f by dou t equals to 0, and then coordinate for f to be constant of motion is obtained to be f comma h is equals to 0. So thus if a function f does not depend on time, which is a constant of motion, its Poisson bracket with the Hamilton's vanishes. In other words, a function whose Poisson bracket with Hamiltonian vanishes is a constant of motion. This result does not depend whether h itself is a constant of motion. Let us see here equations of motion in Poisson bracket form. We will see here some special cases by using equation number 8. Let us go to the equation number 8. So here equation number 8 df by dt, which is equals to dou f by dou t plus f comma h. So let us consider this equation. By using this equation number 8, we can replace here qk in the place of f. That means consider here qk in the place of f. So what will happen? So f equals to qk. So dou f by dou t. So dou qk by dou t is nothing but q dot k. So here q dot k, which is equals to in the place of f, we have to replace with qk. Qk comma h, which is equation number 11a. So in the same way, replace f with small pk. So p dot k equals to pk comma h, and replace f with h. So we'll obtain h is equals to dou h by dou t. So these three equations, that means 11a, 11b, 11c, which are identical to the Hamilton's equation 37a, 37b, 37c, are 40 of the chapter 3, which are referred as equations of motion in the Poisson bracket form. So let us see the properties of Poisson brackets and also fundamental Poisson's brackets. This Poisson bracket has the property of antisymmetry, which is given by, that means f comma g equals to minus g comma f. That means this Poisson bracket has the property of antisymmetry. So here f comma g, which is equals to sigma k dou f by dou qk dou g by dou pk minus dou f by dou pk dou g by dou qk. So this is actually f comma g. So which is equals to here antisymmetry minus g comma f. That means sigma minus sigma k So dou g by dou qk, dou f by dou pk. That means we are alternating here. So f comma g, which is altered here in the same way. Here g comma f. So dou g by dou qk, dou f by dou pk minus dou g by dou pk, dou f by dou qk, which is equals to minus g comma f. That means here the Poisson bracket has the property of anti-symmetry. F comma g, which is equals to minus g comma f. So thus, Poisson bracket does not obey the commutative law of algebra. So as an application of the Poisson brackets, we are giving below some of the examples here. Let us see some of the cases. Let us substitute QL in the place of G. That means already we have the Poisson bracket F comma G. So in the place of G, we are substituting here QL. So F comma QL, which is equals to sigma K, dou F by dou QK, dou QL by dou PK. That means in the place of G, we are substituting here QL minus dou F by dou PK, dou QL by dou QK, which is equals to minus sigma K dou F by dou PK into delta LK. That means here, if we observe here, the derivative dou QL with respect to dou PK, which is equals to 0. So here this term becomes 0. Here dou QL by dou QK. So here, which is here, we can write it as delta LK. When LK equals to, see, let us see here, we have some cases. When here delta Lk or Kl, it is a Kronecker delta symbol with a property delta Kl equals to 0 for k not equals to 1 and delta Kl equals to 1 for k equals to L. That means here for k equals to L, delta Kl equals to 1. We will consider here this Kronecker operation here. So sigma k dou f by dou pk, dou Ql by dou qk, delta Lk. Here L equals to k. So f comma ql, which is equals to minus dou f by dou p. Let us replace L equals to k, no? So we are replacing k with L. So dou f by dou pl. And also if q equals to f equals to qk, that means let us replace f here with qk. So qk comma ql, which is equals to minus dou qk by dou pl, which is equals to 0. So here derivative of qk with respect to p, which is equals to 0. And let us replace f with pk. So here let us consider this equation number 13. F replace f with pk. So pk comma ql, which is equals to minus dou pk by dou pl. So here with respect to p, pk with respect to pl minus dou kl. Here k equals to l. Now let us consider the case G equals to PL. Here already we have considered G equals to QL. Now let us consider case to G equals to PL. F comma PL, which is equals to sigma K dou F by dou QK into delta QL. So here also same in the case number 1. So F comma PL is equals to dou F by dou QL. Here we are replacing K equals to L here. Delta KL equals to here K equals to L. So we are replacing here. Delta KL equals to 1. So if you replace F with Pk, so Pk comma Pl, which is equals to dou Pk by dou Ql, which is equals to 0, equation number 17. In the same way, let us replace F with Qk. So Qk comma Pl, which is equals to dou Qk by dou Ql, which is equals to delta Kl. So these results can be summarized as Qk comma Ql equals to Pk comma Pl, which is equals to 0, or Qk comma Pl, which is equals to delta QL, KL. So that means here same things, QK, QK, QL or PK, PL, which are equals to 0, and opposite here Q and P, which is equals to delta KL. So where here already we have discussed delta KL, it is a Kronecker delta symbol with the property delta KL equals to 0 for K not equals to 1 and delta KL equals to 1 for K equals to L. So here these equation number 19 and 20 are called fundamental Poisson's brackets. So already these are the fundamentals Poisson's bracket. Thank you, children.